Good evening, everyone. Warm welcome to all our members. If you haven't been with us, warm welcome to you as well. Welcome to the Namibia Scientific Society. We also have a few people joining us via Zoom. Warm welcome to those joining us via Zoom as well. Tonight we are going to get an interesting I don't want to call it a lecture, presentation from our two speakers who I will introduce in a bit, turning urine into fertilizer. I'm not going to say much about that, let them do the talking rather. Um, just for those of you who haven't been with us, doesn't know the building, if you go out this door to your right and you follow the corridor, our bathrooms, and then at the back, we have a cash bar. You are welcome to have something to drink afterwards. We work on donation base, so you can donate as you feel led when you purchase a water or a drink. Yes, but without delaying it too much, because I'm sure you have a jam-packed presentation for us, let me quickly introduce our speakers for the night. Let me first start with Dr. Simha from the Swedish University of Agricultural Sciences. He focuses on developing technologies that safely recycle resources from wastewater, contributing to a circular economy in the sanitation space. His specialities lies in urine chemistry and the recycling of human urine as crop fertilizers. Dr. Simha holds a PhD in technology and a master's in environmental sciences, policy, and management, with a background in chemical process engineering. He is also a contributing author to the United Nations Environment Programme's flagship report and serves on the International Water Association's Management Committee for Resource-Orientated Sanitation. Joining him is Mr. Gert van der Merwe. Other than pursuing a PhD at Delft University of Technology, his work explores water and its role in the interconnected relationships between species, technology, and the environment. At the Namibia University of Science and Technology, he serves as the departmental research coordinator and contributes to several research clusters. Both Mr. van der Merwe and Dr. Simha are collaborating with the Namibia University of Science and Technology and the Gobabeb Namib Research Institute on a project aimed at prototyping and evaluating a solar thermal and wind-driven urine evaporator, an innovative step towards a sustainable resource recovery. So without further ado, please join me in giving them a warm welcome and let them take this further. Thank you.
Good evening, everyone. Can you hear me well? Okay, good. I'm just happy to see a room full of people who are interested in urine as a topic. So I hope that at the end of our talk, you'll be as fascinated with urine and urine chemistry as we are. So I'm from a research group in Sweden called Kretslopp's technique. So literal translation is circular and environmental engineering. I've been working in Sweden at this university as a scientist for the last 10 years, focusing on urine. And in my research group, we look at domestic wastewater quite differently, away from the status quo. So we are proponents of a concept called source-separated sanitation. It's something that I came across when I was an undergrad student in India, something that I read when I was looking through papers on wastewater treatment. And once I read about it, I couldn't get it out of my mind, because at the core of this concept, the idea is so simple. It says that in our houses, we produce different fractions of wastewater. We produce human urine, produce feces or brown water, depending on whether our toilets are flushed, gray water from our kitchens and bathrooms, rainwater, stormwater runoff. So physically, chemically, biologically, and even in terms of volume, all of these fractions are so distinct. But the modern way of doing sanitation is that we mix all of them together and send it in one sewer pipe to a centralized wastewater treatment plant, where we hope that this complex mixture of chemicals and pollutants is somehow purified into water. But we all know that the best we can get out of it in most cases is semi-purified water, which is, for me at least, a fancy term for wastewater effluent, because we've removed pollutants from our water to a certain degree, but it's not drinking water quality. And that's why in most cases, in most cities, these effluents are then diluted into rivers, into lakes, into dams, because then they get mixed with fresh water, thereby reducing the risk of disease transmission in our society. So source separation argues that because each of these fractions are so distinct, why don't we separate them at source in our houses? And why don't we treat them separately so that we have an opportunity to safely recycle them into value-added products? And that's something we already do in terms of solid waste management at our homes, don't we? We separate plastic, metals, food waste, and we do that because if you mix them, the only place they end up is a landfill or an incinerator. But if we separate the metals and the plastic, we recycle them. So personally, I got really interested in urine chemistry because urine is a very interesting matrix in its own, because we only produce in our household, only 1% of the total volume of wastewater that comes out is urine. But that 1% contains 80% of the nitrogen and 50% of the phosphorus and potassium. So these are the same nutrients that our wastewater treatment plants use energy and chemicals to remove, not recycle. So even though urine is such a small fraction, it's not as easy to recycle. You can collect urine and use it as a liquid fertilizer, but you can't scale that approach at a city scale, right? Because urine is 95% water. So even though it's such a small fraction, it's mostly water. And the reality today is majority of us, we live in cities, we live in urban areas. So how do we get urine, which is mostly water, from the city center to rural cropland where the majority of the food is grown today? And depending on where we live in the world today, these distances between urban and rural cropland can be a few kilometers, for example, in Uppsala, where I live, to a few hundred kilometers in New York and Boston. And that's the reason why we don't recycle or transport liquid urine from the city to rural cropland to be used as a fertilizer. So at SLU, at our university, we started thinking, what can we do with urine at the source, where it is produced? What can we do with urine at the house? Is there a way we can somehow dehydrate the urine so we get rid of the water in the urine, so that instead of collecting and recycling 500 kilograms of liquid urine per person per year, we recycle only 20 kilograms of dried fertilizer? So on paper, it seems simple, right? Like, let's separate the water, let's collect the nutrients, let's use it as a fertilizer. So we started investigating that and realized that when we excrete urine, the pH of urine is neutral, around neutral. So it's between 6 and 7 for an average person. But once urine goes through our toilets and through our sewer pipes, we have a few reactions that happen that convert urea, which is the main nitrogen compound in urine, into ammonia. And so this reaction produces ammonia, which is a base. So it also has a side effect of changing the pH of urine from 6 to 7 to around 9. And that's important because at that pH, the ammonia that is produced by the reaction now is volatile. It's a gas. So if you've been to a dirty bathroom or a bathroom that hasn't been cleaned often, the smell that you get from urine, that's essentially majority is ammonia. And that's because it's a gas. So urease, this enzyme, it's present everywhere in the environment. It's ubiquitous. It's in our skin. It's in our skin bacteria because the bacteria produces urease. It's in our saliva, in our feces. It's in our soils. So when a farmer is applying urea as a chemical fertilizer, this enzyme is actually very beneficial because it converts urea into ammonia, which is a form of nitrogen that plants can take up for nutrition. But in a sanitation system, like a source-separated sanitation system where we want to recycle urine, this enzyme is a bit of a nuisance because it takes urea, which is a non-volatile compound and the most widely used fertilizer in the world, and it converts it into a volatile form, ammonia. So if you try to dehydrate urine that has already been hydrolyzed, where majority of the nitrogen is now ammonia, you lose the ammonia as a gas. So we started looking into the enzyme chemistry, realizing that several bacteria that colonize the pipes in our sanitation system that produce these enzymes, they have a very narrow range in which they can operate, like most living organisms. So they have a very narrow pH range within which they are active. So if you shift the pH of urine, of freshly excreted urine before it goes through our sewers, if you shift it below 3, so you acidify it, or you increase it to above 10, alkalize it, you can stop the enzyme from acting. So you inhibit the enzyme. So that even if the enzyme and the bacteria is present, it remains dormant. So it means it can't access the urea. So we then started looking at what chemicals or additives can we add to the urine in order to shift the pH of the urine and make it stable. And we say stabilizing urine because we are stabilizing the urea in the urine so it does not convert to ammonia. And after several years of experimentation, research, trials, we developed something which we call Nutrifix. So Nutrifix is a blend of organic acids. For example, citric acid from lemons. It's a blend that has been carefully selected in order to optimize both the dosage of the chemical we add, but also to shift the urine pH to below 3, but also it's also optimized for cost. So over the last few years, we've optimized it to an extent that now we only have to add a few grams of Nutrifix to every liter of urine so that it stabilizes the urine. And for a person to have enough Nutrifix to stabilize the urine for a whole year, we estimate the cost to be less than 100 Namibian dollars. So meaning it's affordable to a wide segment of society. So that's more or less the chemistry part of this talk, where only thing that I think I'd like everyone to remember is you have freshly excreted urine before it goes into the toilet or into the sewer pipes. If we acidify it, we stop biological reactions that we don't want to occur so that we can keep the nutrients in a stable form so that we can then evaporate it. So if you dehydrate urine that has been pre-stabilized with Nutrifix, you recover more than 99% of all the nutrients that are excreted in the urine. So how do we do this in practice? So to collect and dehydrate freshly excreted urine and to produce a solid fertilizer, you need to do 3 steps. First, we need to somehow collect source-separated urine, separate from the rest of the fraction of wastewater in the house. Then you have to add Nutrifix in order to stabilize it so that the nutrients are not degraded. And third, you just have to evaporate the pre-stabilized urine. So how can we collect source-separated urine? We can collect them in buckets and jerry cans, which is the norm in many informal settlement households in Namibia, in India, and globally. We can use male urinals that are in many properties already in society, but we can also use female and unisex urinals, which we also have developed at our university, which we've also tested with thousands of participants at festivals in Sweden, where men, women, children, regardless of gender or orientation, can use the same urinal. But we can also use something called a urine separating toilet. So the picture and the animation that you see is of a modern version of a urine separating toilet, because these toilets have been around for several decades already. But the invention or the genius of this idea is that it looks like a conventional mixed toilet, but it has a trap that is invisible to the user. I don't know if my pointer works, but So there is a trap over here that is invisible to you as a user, which separates the urine using something called the teapot effect. And thank you, Hans, for this. So the teapot effect essentially uses surface tension. So if you're trying to pour tea using a teapot, if you pour it slowly, it follows the curvature of the teapot and it comes back to you. But if you pour it strongly enough, it goes into your teacup, right? And that's exactly the principle that this toilet uses. The flow rate at which we urinate is much lower than the flow rate of the flush water we use for washing the toilet bowl. So just because of that, you can then separate urine without much behavior change, because it doesn't matter if you stand, if you sit. It's ideal if most people sit, because then you collect the maximum amount of urine. But on average, you can collect 70 to 80% of the urine using this toilet. And as soon as you collect the urine, before it goes into the sewer pipe, we have to add Nutrifix. So this is a toilet that we developed and have installed in Sweden, where below this wall-hung toilet, we've installed a cartridge. And inside the cartridge, we dose Nutrifix. And Nutrifix, the chemical blend of organic acids, it's also packaged in a water-soluble biopolymer pouch, very similar to how we use dishwasher tablets or tablets for washing our laundry. So it's packaged so that the user does not have to touch any acids, but at the same time, as soon as it touches urine, which is water, it dissolves. So step two, we've done that, right? We've added Nutrifix into the cartridge so that urine, as soon as it comes from the toilet, it gets stabilized. And step three is essentially drying, which is the easiest part of all of this process, where we just use a fan and existing ventilation in the bathroom, because in Sweden and in many countries, we have, by law, we have to exchange 4 times the volume of the bathroom air every hour. So you already have forced ventilation in your bathrooms. So all we do is channel the air through the evaporator and then push it out of the bathroom. So thereby we don't use extra energy, apart from a little bit of the pressure drop that you expect from passing air through this. So the end product out of all of this process is that dried product, a dried powder, which we call granurine. Granurine being granulated urine. So because we remove 95% of the water, all we are left with is a dried powder that has up to 20% nitrogen, 2% phosphorus, 5% potassium, carbon because we dose it with organic acids, sulfur, and everything we eat is essentially excreted. All the water-soluble waste of our body is excreted via urine. So all the micronutrients that we consume in food are also in this dried product. So compared to chemical fertilizers that we buy at Agra or wherever, dried urine is a more complete fertilizer because it not just provides macronutrients, it also provides micronutrients. And it is possible for us to remove just 50% of the water or 90% of the water in urine and make concentrated liquid fertilizer that we can dose or use as a fertilizer. But we fully dehydrate urine and granulate it. So the powder that you get from the toilet, we granulate it like urea is granulated into prills. And that's because if you own a big farm with 100 hectares of land, you wouldn't be applying a liquid fertilizer. A liquid fertilizer is great when you're fertilizing your flower pots, but if you want to shift chemical fertilizer use at industrial scale, we need an industrial fertilizer that works with existing machinery. So that's why we granulate the urine, so that in terms of diameter, it's between 2 to 4 millimeters. It's strong enough that it can withstand the machine, which is a combi seed driller. A combi seed driller is something that drills the seed and the fertilizer together using pressurized air. So at preset distances and a preset dose of the fertilizer and the seed, it keeps drilling the soil so that the fertilizer and the seed are drilled below the soil surface in order to give the best start of life for that plant. And granurine can then also withstand the pressure that you would expect from this pneumatic drilling. but also because it is hydrophilic, because it has water-soluble waste from urine, as soon as you irrigate or there is rainfall, it dissolves rapidly. So we've tested this over the last 4 years in Sweden, where we collaborate with farmers who grow barley. So we collect more than 50 meter cubes of urine every year at festivals, at public urinals. We take that urine, we stabilize it on site at the festival where it is being produced. We dehydrate it, granulate it, then give it to barley farmers who grow barley for us. And over the last 4 years of multiple croppings, we've shown that the urine fertilizer has no effect or no negative effect on the barley yield compared to a chemical fertilizer, the NPK that you see there, and obviously much better than the control where you don't add any fertilizer. The barley that is then produced is malted by a local brewery called Gotland's Brewery, and they also then produce the circular beer, which is then also sold commercially in Sweden already as a consumer product that can be bought. So we're we're showing that it's not just research, we can do this in practice. And if you have all the actors in the service chain, you can actually close nutrient loops in society. So, but just because we have a consumer product doesn't mean that people are going to accept it, right? So it's a question we get asked quite a lot. So we did a study ourselves. We looked at more than 5,000 participants on an online survey across 15 different countries to gauge what would be their potential willingness to buy and eat food that has now been grown with urine. It's a strange question to ask because when we're buying food at a grocery store, we don't really ask anyone whether we applied pig manure or cow digestate or whatever. So, but it's a question that we get asked quite often. So we did that study and we found that at least on average, and this is such a hypothetical concept, right? There is no commercially available dried urine that you can buy or food that has now been fertilized apart from Sweden. So even in this initial willingness, we found that at least 60% of the people are open to that idea. So much more than most people would think. We've obviously done a bunch of experiments and studies looking at the safety of the fertilizer. We've looked at a range of bacteria, viruses, helminths, parasites, even antimicrobial resistant genes to show that the fertilizer, this urine that we produce, actually meets most of the global wastewater recycling guidelines already today. So it meets US EPA rules, it meets World Health Organization guidelines. And we just found out this week that the EU, which is notoriously conservative in terms of certifying and regulating any fertilizers of human origin, they've also agreed to certify the fertilizer. So next year in 2026, in April, the EU is now going to allow the sale and buying of urine as a fertilizer, meaning farmers can then commercially buy this and already start using it. Another question we get asked quite a lot is, what about micropollutants in urine? Where do they end up, right? So we did a study, again, with the same barley farmers that we collaborate with. We collected more than 20,000 liters of urine from public urinals across Sweden in order to get a representative sample of what a micropollutant contamination in reality looks like. Because if you look up most studies on these topics, they're all laboratory-based studies where you take urine and you spike it with extra amount of micropollutants. So you don't really realize what the real dose of micropollutant contamination is. So we collected real urine from a representative sample of average Swedish urine, and we screened them for 40 different pharmaceuticals that are most commonly used in Sweden. We did detect 7 out of these 40 pharmaceuticals in the urine, as well as the dried urine that we produce. But the concentrations of these pharmaceuticals are at nanogram per gram level, which means it's at least 100-fold lower than the pharmaceuticals that are already present in our cow manure, as well as sewage sludge, which is produced by our wastewater treatment plants. And both cow manure and sewage sludge is already used globally as a fertilizer. So the conclusion from the study was yes, there are pharmaceuticals, but the concentrations are at such a low or extremely low level that as a consumer risk, it's quite low, because we tracked the fate of these 7 pharmaceuticals along the full food chain to show that we couldn't detect it in the soil, in any parts of the barley, in the kernel, or the malted barley and the beer that is now on the market. And that's also quality assurance that the brewery also needed in order to put the beer on the market. So how can we how can we recycle urine in practice? Because we've talked about the science, we talked about how we do it in Sweden, but how do we do this in reality, in practice? So this is a toilet that we put together in a couple of hours, 8 years ago, when I first started my PhD. It's a urine separating toilet manufactured in Durban by a company called EnviroSan. So local urine diverting toilet manufacturers do exist here. And it's just a box containing Nutrifix, the chemical that we've been dosing. Urine comes in from a pipe. Using existing ventilation, it gets dehydrated. Over time, every day, urine keeps coming in, keeps getting dried, keeps enriching the final product until you have to harvest it. But we've done technified approaches also about this. But the reality is that in Sweden, more than 90% of the households are already sewered. So for us, it's a struggle to figure out where can we collect enough quantities of urine from. So one of the first things we looked at was existing households that were built, or buildings that were built in the 1960s and 70s that are now due for renovation. So people don't switch toilets that often. So you have to wait until you're at that cycle. So we built a toilet, which we installed it at the offices of a wastewater treatment plant in Malmo, where all we did was we took out the old toilet, put in this new Laufen urine separating toilet that separates urine with the teapot effect. And we developed a cartridge that can go below this existing toilet so that it doesn't use extra space in the bathroom. And in that cartridge, we load Nutrifix pouches. So every day, so the cycle works like this. At the first day, we load the cartridge with enough Nutrifix to last for a whole month. So every day urine keeps coming in, keeps getting stabilized, and using a fan and existing ventilation, it keeps getting dried. And at the end of 1 month, when we've run out of Nutrifix, so the whole system is digitized. So we know what level of urine we have in the containers. In case there is a party, there is an overflow function. So at the end of that month, you get a warning saying in a week, it's time to harvest the dried urine. And at the end of that week, you get a red warning, so you can't use the toilet anymore, meaning you can still use the toilet, but the urine does not get collected in the cartridge. So the end product, when we remove the cartridge, is fully dried. And to start a new cycle, you remove the cartridge and put in a new cartridge with Nutrifix. We've looked at public urinals because that's again a big space where we can collect urine. So this is a modular urine evaporator where one part of the system is a reactor where we dose Nutrifix. So urine keeps coming in from the urinal, keeps getting acidified, and keeps getting dried into that drawer, which we can then pull out to collect dried urine. And this is a system we've actually installed at our university. So if you do visit, you get to use this. We've also built a mobile urine concentrator. So because festivals happen in remote places where thousands of people now congregate, where there is no sanitation, what do we do there? So we can install urinals or urine separating toilets, very similar to what you do at a construction site. You bring the toilet to the site, but instead of then bringing urine from that site, which is the volume, because we don't want to transport water, we've developed this mobile concentrator that we can then go to the festival, collect the urine, concentrate it to remove 90% of the water. So the urine is still a liquid, but now we are dealing with a tenth of the mass. So that is then pumped into the first, into the IBCs, the 1,000-liter cube, 1,000-liter tanks, where we bring the concentrate back, and we bring it back to Sweden's biggest cement manufacturing plant, which so the kiln of the cement plant releases hot air that is at 300 degrees just into the atmosphere. So it's waste heat that we can actually use for a bunch of things. So we asked them saying, can we use their waste heat? And they were like, yes, go for it. So we installed a pipe to take that 300-degree heat, blend it with ambient air, which is at 25 degrees, in order to create a stream that is now at 100 degrees, which we can then use to evaporate urine. So meaning we can use existing waste heat in many facilities, not just a cement plant, for example, at data centers, where there's a lot of heat being produced and a lot of water being used to cool these systems down. And the flagship system that we've installed this year is at a football stadium called Studenternas. It's in Uppsala, where I live, and it's in the middle of the city, very close to the town hall, where approximately 7,000 people go and watch football games every weekend. So what we did in collaboration with the municipality is we swapped all the existing mixed toilets, the one on the left you see, with the Laufen urine separating toilet. And we already had male urinals across the stadium. So in each of these rooms, there are 30 of these rooms where people go and urinate and use the toilet. So in each of these rooms, we installed a small reactor, the stainless steel containers that you see in the pictures, where we dose Nutrifix. So urine from the toilets gets collected. Once it gets filled up, all the urine from different parts of the stadium are then vacuum pumped to one shipping container at the end of the stadium, where we then concentrate it and produce a fertilizer. So we have a whole week to dry the urine because we are only hosting football matches every weekend. So overall, the process is you add the stabilizer, the Nutrifix, in order to make sure nutrients stay in the urine. We dry that urine, then we can dry it either fully or pre-concentrated to remove 90% of the water, so that concentrates from different buildings, the football stadium, public urinals, can all come to one production facility where it's now fully dried and granulated. And thereby you also assure product quality, because each of us eats different food. So we produce different nutrients in our urine. But if you collect it from enough people, on average, you have the same composition. But overall, the bigger picture is how much impact can we have by recycling urine globally? So the answer is a third of the chemical fertilizer that we use today can simply be swapped with urine recycling. So urine can substitute 30 to 40% of the global nitrogen and phosphorus fertilizers that are produced synthetically or industrially. And depending on where we live in the world, this replacement potential can be 30%, for example, in Namibia, but it can be more than 100%, for example, in Kenya, in Uganda, where also in India, in several parts where you have a lot of subsistence farming. So the access to chemical fertilizers is low and chemical fertilizers are expensive. So farmers don't use chemical fertilizers. In that case, dried urine or any urine-based fertilizer can actually improve crop productivity using the same land. So in many countries, you can actually double or triple the food production just by recycling urine within the same spatial footprint. So before I hand it over to Herb, I have one thing I would love everyone to remember, is that the urine that we produce every day, each person, it has enough nutrients to grow enough wheat to fertilize enough wheat to have a loaf of bread. So next time you go to the bathroom, every time you're peeing, you're essentially peeing a loaf of bread away. Yeah, thank you.
Thanks, Prithvi. Prithvi gave you all the science, and as an architect, I'm more interested in application, and that's essentially where our collaboration started. So, just to put it into context, I'm an advocate for. It's great to do this in Sweden, but what about the rest of the world? And that's where I'm a huge advocate for the global south. So in the top right-hand corner, top left-hand corner, you can see the graph for displaced peoples that has tripled since 2011, and largely that is due to drought and water scarcity and food scarcity, which then has knock-on effects. So and we're not too far removed from that if you look at our own food security and our own water security. So that's where my interest started. And that's why I believe that as an architect, with more than 1 billion people living in slums, we should really be focusing there. And at the bottom right, on the right-hand side, you can see an image from the Namibia Housing Action Group, which is an NGO operating here in Windhoek and well across the country. And in one of the neighborhoods, it's actually in one of the neighborhoods that we're working in with us, which is unsewered. And this intersects with a lot of things, including it's not just food and water security, but also housing, because you can't get a house without sanitation. So that's how I entered the space. But I'll pause it there because I'm sure most of you aren't interested in the urban questions per se. But essentially, if we then start thinking about like all these people live in all these decentralized places where we'll never get sanitation, or at least sewered sanitation. And if we also look at who are the farmers that can't afford fertilizer, we'll notice that the vast majority of farmers are actually smallholder farmers, so people that have 1 to 2 hectares of land. And these are typically people in the global south. And these are people that are vulnerable in the sense that they can't afford fertilizer. And it's particularly these people that would also then be displaced. So that's essentially where our collaboration comes in. And this box you can see in the front here is meant to address that problem. So it's not about formalized settings, although we are interested in that as well. But to really have an impact, we really need to think about decentralized urine collection and drying. So that's where we started. Now bringing it back home to Namibia, if we look at our own catchment zone here in Windhoek, this is what Swakopmund looks like. This is data from NamWater, and they track this extensively. And most of you will be aware that actually we're in a closed loop. So if you look at the bottom right-hand corner, you'll see that we have 3 dams. Koryangap's already unusable. Swakopmund's our main holding dam, and everything that flows down our rivers ends up there. And then we pump it to Vonbach and to Windhoek. So this is an existential crisis for our own water security. And a large portion of this is actually the nutrient that ends up in the water and goes to Swakopmund in the long run. So it's not just about about food security. It's not just about people's housing. It's also about our own water security as we sit here. And just to drive it home, it costs 10 times more money to remove nitrogen from water than it costs to produce that same nitrogen in the fertilizer. So we really need to keep it out of our water, right? And that's where all of this came from. So we conceptualized this idea and we said, okay, what do we need to do? It needs to be something that's extremely simple, extremely affordable, and has no moving parts, doesn't rely on electricity. So that's this box that you see in front of you here called the AirCloset. So instead of a water closet, it's an AirCloset. And basically, as an architect, I just drew up a quick CAD drawing, and then we went about doing the technical investigation at GoWeb. So how we did it is you'll see there's a tray in here. We inserted a weighing scale, as well as monitors for temperature and humidity in various parts of the evaporator. And then we monitored this in 5-minute intervals so that we could track how it was performing. And then if you look over here, you can see sort of the typical daily when the sun hits the evaporator, and then it drops down. And you can also see the relationship between humidity in the box as well as temperature. And also the bottom at the bottom, you can see how the temperature of the box heats up based on the direction of the sun over time. So you'll notice that on the southern side, it's significantly cooler than on the north, east, and west. And we then tested this in 10-day cycles. And because it evaporates about 5 liters per square meter. So we loaded it up with 50 liters of urine and then let it evaporate all the way through. So that's the graph that you can see on the left-hand side, and we kept on repeating that cycle. And you can also see on the top right, on the right-hand side, you can see the hourly rates in terms of loss. So that's how we were tracking it and kind of iterating a little bit. So here you can see that initially we started off with a really big vent and a whirlybird on top, because we thought that ventilation is going to be important. But we soon found out that actually that ventilation rate was way too fast and we were losing all the heat. So we constrained the vent pipe. You can also see on the sides, we had vent pipes that we set up such that we could allow for more ventilation or less ventilation and test that, as well as in the front. And then on the right-hand side, you can see the product when it's almost dry, and then when we take out the plastic sheet when it's fully dried. We then continued iterating a little bit more. Also, I might add also that we found out that insulation is really important. So we then iterated a little bit more. Prithvi was already involved in a project in Ethiopia. And based on what we had been doing together, he suggested that I should join the project. And very soon we asked one of the PhD students to continue iterating. So this is a multi-tray system that was tested in Ethiopia. We find that it's not the most ideal because it's a little clunky to get things in and out, etc. So it's better to kind of stick to simple stuff. And that was sort of the technical investigation. Then now we're at the phase where we've done a bunch of interviews. We've surveyed 150 households, and now we're entering sort of dialogues. So this was at the National Urban Dialogue 2 weeks ago, which was within the Ministry of Urban and Rural Development, hosted by GIZ, where we displayed it and we discussed how it works with people. We also took the unit to a shebeen in Katutura and asked someone, can you replicate this? Because that was really important to us, that it wasn't something that was technically too difficult for anyone to replicate. And that it would be accessible to people in informal settlements. So here you can see the process from just folded sheets, adding the sides, doing the frame at the top, adding a mesh, painting it, etc. And here you can see the proud. Sorry, Vibke, I'll go back for you to take a picture. Here you can see the proud contractor who had been enlisting other people along the way. He was very adamant we should take many pictures of him, so he was posed. Then we went about identifying sites where we could install them, because we'd done all the groundwork, interviews, surveys, etc. But now we need to really see how it will work in the real world. So that's where we are at the moment. So we identified 10 sites, and today I will show you 4 sites. This is starting with a small household scale sort of level, and then moving up to a garden, a person with a garden, then a community garden, and then a much larger scale one. So starting off in Pitananyemba, this is the neighborhood that I showed you earlier where that riverbed was so polluted. And we first scouted for where could we find urine. So these are all makeshift urinals. at various shebeens, et cetera, et cetera. So we were looking at how could we potentially collect urine in these contexts. We also looked for other opportunities. So for instance, we noticed that people were already transporting water in containers quite easily with little, what do you call those? Little trolleys. People have their own community gardens. This is your work. And then we did the first sort of installation. So here you can see us. We put down the first evaporator, and we were discussing with people how to go about it. And this is really just at a household scale. Now, bear in mind, in this context, people often don't leave their house in the evening for safety reasons, and they collect their excrement in buckets. Now, that's not the ideal. That's not how we would want to continue in the long run. But for the time being, while we're testing, we're asking them, instead of throwing it in the river, please just throw it in a container, and then when the container is full, decant it into the evaporator. Moving on, we found a wonderful site in Rebot, which was much easier than Pieter Nanyemba because it's nice and flat. And it's not rocky, so it's easy to put down the evaporator. It's fenced off, etc. So this is our second site. This individual is also training other people in the community to grow their own vegetables, and he was very, very eager when he heard about the opportunity to turn urine into fertilizer. So we hadn't originally planned to work there, but he was so enthusiastic that we decided, yes, we'll do it. So here you can see how we're cutting the sheet. We're showing them how to cut the sheet of plastic, how to put it in the tray. Then you can see how we're using a siphon to decant the urine. And mind you, I might add, there were only 2 people in the household, and he filled this 25-liter can in 3 days. So I'm not sure how he managed to do that, but he was very eager for us to come. So we came and we showed them how to decant it and so on. And here you can see the proud owner of the AirCloset in Rebot. Now moving to a slightly more complex context. In Kabila C, I've been working with this community over a longer period of time. They have a small community garden where they ostensibly actually children how to do gardens, and they're trying to do urban greening. They plant trees, etc. It's a very tough area because, as you can see, there's no topsoil, etc. So to really reestablish organic matter in this context, very difficult. So I asked them whether they would be interested in having 2 dryers. So as a collective, they are then collecting urine and decanting it in there. And here you can see our installation. In this context, we were slightly more concerned with vandalism and theft because it's in a public space. So we chained the 2 together. So it makes it significantly more difficult to move. But we'll see whether that's necessary. The first case was also at an intersection, and there we chose not to chain it down to see whether someone takes it. So that's a small experiment to see whether people will take it. And here you can see how we're showing people the whole process and a Q&A session. So this is the core group in this neighborhood. Then moving up a scale, we're also working in Osiri refugee camp. So first we scouted to see what the context was. So on the left-hand side, you can see their water supply. In the middle, you can see their the manure that they're using, as well as all the crops. So we first wanted to understand how that worked. And in this context, we don't actually need a movable unit. So I forgot to mention that this unit has to be movable for informal settlements because there's something called reblocking. That's when people go from living in shacks to owning their land. They need to be able to move their house. So they're not allowed to build with any permanent structures. So that's why this unit's also designed such that you can move it. But in Osire, this is not a problem, so we could go for scale. So we're working at a school, which allows collection to be much easier. And here we decided to then build them with bricks and see how that's operating. And this allows us to significantly increase the surface area. So where this one has a surface area of about 1.8 meters, each one of these units you see over here has a surface area of about 6.5 square meters, and that allows us to deal with about 150 liters a day. So that we hope, we think, we'll monitor this one. But it's much cheaper than this unit, even though this unit is already relatively affordable. We've calculated that the value of the fertilizer would offset the cost of one of these evaporators within a year, max 3. Even at bulk prices. So here we were simply building them with brick. We were showing people how to make frames, put polycarbonate on them. Unfortunately, the direction of the polycarb was put in the wrong direction because the hinges were welded in the wrong place, but we'll deal with it. And luckily we found a space that was also fenced off because we didn't want the children to go tinker with our experiment. And then here you can see 2 of these units, as well as the brick units that we have in this space. So we hope that we can essentially evaporate 150 liters a day, which is about 100 people's urine, daily urine. So that's quite a bit. And just looking at thermal imaging, comparing the AirCloset like this one on the right-hand side to the brick units on the left-hand side, you can see that the temperatures are similar, so we are fairly confident that we will get similar performance. So with that, I want to thank everyone for your time. If you have any questions, you're welcome to visit our website. We created a small website with FAQs as well as links to all the research. So in case you're so inclined to really dig into the research, then all the papers are there. And I also want to invite Prithvi to pass around the sample of granurine. So that little sample is 5 liters of urine concentrated into 100 grams. So with that, thank you. And if there are any questions, now is your moment. Thank you. And thank you to the Scientific Society.
Are there any questions?
Yeah, from a practical, my name is Röschlau. I'm a member of the society. But from a practical point of view, I don't think it's easy to separate the liquids from the solids so that you can use the solids freely. I don't know how you do it in India, but here it won't work. And we are much more concerned of finding toilet facilities in the rural areas and so on, instead of putting up a fancy thing like that. Solids and liquids? Well, if you go to the toilet, yes, you have solids and liquids. And that's the theory, yes. But in a normal household, you don't have enough space for 2 different ones, and then jump from the one pot to the other, because all of a sudden you find that you no, come on.
So it's just one toilet, and the one toilet already separates the urine from the feces. So, but there are 200,000 of these toilets in Sweden already, but they're already manufactured at scale in Durban. So Envirosan, the company that manufactures these toilets, produce 1,000 of these toilets per day. So they're already distributed all across Africa, all across India. So they've existed for 40 years. It's just that the design of the toilets has kept getting iterated to make it more comfortable as a user experience.
Any other questions?
So you guys talked a bit about human waste, but what about non-human waste and scaling it to issues, agriculture, dairy farming, livestock? Are there any issues with using animal waste that would pose any translation problems, or is all these principles translate the same?
Do you mean what if we collect cow urine and pig urine separate? I mean, it's a bit difficult. I mean, we can train people to go and pee in the right place, but there are toilets that can separate cow urine from the rest of the cow. They've been tested both in the Netherlands and in Copenhagen, in Denmark, where they've tried 1,000 of these. I don't know how well they work, but in theory, yes, as long as, but the chemistry remains the same. Human urine and cow urine, compositionally, they're very similar. So urea is the main nitrogen compound, even in cow urine, as well as human urine. It's just that they produce per day and we produce 1.5 liters per day. So chemistry-wise, the principle remains the same. If you can somehow stop the hydrolysis reaction from happening, you can still recover nitrogen as urea instead of ammonia, because that's what happens when you try to apply cow manure or cow digestate even as a fertilizer. You lose quite a lot of the nitrogen as ammonia. So by keeping it as urea and then drilling it into the soil, you prevent the volatilization from happening.
I also just want to respond to the statement earlier. So there's a lot of people that have invested in urine separating technology already, particularly people who are interested in composting toilets because they want to dry the fecal matter. Including in Namibia, people have made them right here. So this is technology that exists, and simultaneously, it's very easy to divert urine from a urinal. So that's 50% of the population already separated. And 50% separation will double the capacity, the treatment capacity of a sewage treatment plant. So even if we just separate the urine from urinals, the impact on the treatment capacity of the formal sector will be incredibly high. So I just wanted to respond to that.
Thanks, Gert. I have a technical question. Why are you using like the clear? And wouldn't it also dry even faster if that was a black top and get very hot in that? Why does it have to be, or why are you using the clear?
So we want the urine to heat as much as possible directly, and we don't want to heat the air as much. So if it was black, you'd be heating the air, and that hot air would be staying at the top, and then we're not heating the urine. So we want the light to hit the urine. So ideally, actually, we would want to make the whole thing out of plastic. Oh, no. Temperature is very important. So there's a triple barrier for safety, right? So the first is a dosage with a acid. That's the first safety protocol. The second is the temperature. So we get a temperature of around 60, maybe 70. So as high as possible, because that pathogens that are in the urine. So typically urine should be safe to handle as is, but there's always a risk of cross-contamination. And then the third layer is the dehydration, because it's all salts, and that kills pathogens. So that's the triple barrier that we're using. Unfortunately, with this design, we can't rely on UV. So UV would be an additional safety barrier, but because polycarbonate is UV resistant, we don't get that benefit there. So glass would work, but glass is also much more fragile.
So I just wanted on that temperature thing. So it can go up to boiling point. You would not that wouldn't change the chemistry. Okay.
The urine will never really boil because as it evaporates, it's losing heat, right? So exactly. So we are actually interested in testing a more complex system to reduce the footprint and deal with much higher volumes. So this would be for something like shebeens or bars or whatever. And there we want to actually heat the urine directly. So we're not heating air. In this case, we also actually need to reduce the volume within this box to get better efficiency. So we've just stuck to the same design that we had for GoBip, and there we actually created space so that we could get the scale in. So actually, we want to reduce the volume of air in the space. So yeah, there's a lot to be tinkered with still.
I can see that the design is more or less like a solar water heaters, and if I'm not mistaken, is at 80 degree. If I'm not, is it at 30-degree angle? And I suppose it must face the north to have this maximum emission. It's more like a solar water heater. Okay. So and you said in summer, what the evaporations is it in terms of evaporation percentage-wise? Is it at what percentage is the evaporations?
Is it a question about rain? Okay, so that's where if you look at this system. Here we actually have a polycarb sheet on top of a corrugated polycarb sheet, and that's essentially to create an air gap so that if we have cold water hitting the surface, it's not cooling the surface, the air inside the box. So it's creating a double paned window without having to fork out money for double glazing. Does that answer your question? Oh, and on average, 5 liters per square. Per day. Okay. Yeah, so as it heats up, it extracts heat. Yeah, it should work. I mean,
so we tested this at GoBib for at least 9 months, I think, overall, where even when you had fog coming in. So even then, you still get 2.5 liters of evaporation per day per meter square, because as long as you have enough sunlight coming in, for every degree increase in the air temperature, you double the capacity of air to hold moisture. So the higher the heat retention, or the more the heat retention in the system, the more is the evaporation. So overall, what we've seen is a range between 2 liters per day per meter square to around 8 liters per day per meter square, depending on summer and rainy seasons.
Yeah, thank you, gentlemen, for your very interesting presentation. I had to come when I saw the title. I'm very far from this science topic, but definitely it intrigued me. If I were a farmer and you know, and I heard about this, I mean, the whole concept is strange already, using urine for crop production. And what would make me invest in this fertilizer versus existing commercial fertilizers, you know, for my farm, you know, and for my production? What would be my motivation for investing more in this?
Price. No, but well, so Prithvi can also speak to sort of the Swedish context. It's funny. Our experience here has been that it's usually people actually that have an agrarian background in the city that respond very positive positively to it. And part of the incentive here is I want to buy a toilet, right? So that's where people start, is like, oh, I can turn my urine into something with which I can actually build a toilet, right? So within 5 years, your urine will pay for a toilet. So that's the basic economics of it.
But just in terms of it being a fertilizer, you have a complete fertilizer which you wouldn't have if you're just buying urea at Agra. So urea only supplies nitrogen, but phosphorus is the second most limiting crop nutrient. But you also have potassium and all the salts and all micronutrients we eat. So if you just add dehydrated urine versus a chemical fertilizer, you also have biostimulants in urine that we produce. So we have phytones that we produce and excrete in urine. So they are crop stimulants. So you actually can underdose your dehydrated urine in terms of nitrogen application. So if you were applying 200 kilograms of urea per hectare, you don't have to apply the equivalent amount as dried urine. You can underdose it, but still get the same crop performance. The second thing which we didn't add is that the whole fertilizer, first of all, it's bio-based, right? It's a biological resource that we're recycling safely. But also because we also add organic acids, so still it's an organic fertilizer, although most organic association wouldn't think of it as an organic fertilizer, because chemically it behaves like urea, right? So it's a fast-acting fertilizer, but it's bio-based in nature. The third thing is it's carbon negative. So it's not carbon neutral. The fertilizer actually will lock more carbon than we put it into the process. So we've done life cycle analysis studies to establish that because we avoid wastewater treatment in the city, but we also produce fertilizer, which means we avoid emissions from synthetic fertilizer production. You have this double gain, which means the whole process is carbon negative. So as a farmer, you can then say that you're contributing to the climate movement. Yeah, otherwise it's price. Yeah.
For this specific type, when do you add Eutrophic to stabilize the urine? Do you just dump it like? Oh, okay.
Yes, exactly. Yes, exactly. And we add 100 grams of Nutrifix for the whole 25 kilos of urine that comes in. Because it's water soluble, as soon as the first urination happens, it dissolves, so that any extra urine that keeps coming up every day is already stabilized. So once your jerry can is full, you pour it into the AirCloset. The other option is, if you have a urinal that you're connected, that you connect with the pipe to this system, you dose the acid into the tray. So you dose enough Nutrifix for 200 liters to come in. And once you know that 200 liters has come in, then you harvest the dried urine. No. Exactly.
Not just the smell, but
Yeah.
the nitrogen. You're losing the nitrogen through ammonia. So you're losing the value through the nitrogen that's evaporating, right? So it's the value in your fertilizer that you're losing through that. So yes, smell is also of concern for the user, but from the economics perspective, it's really to prevent the nitrogen loss.
I don't know whether you actually mentioned it here, but I know that we talked about this. Your model is people can actually sell this. No? That's where you said about recovering the cost, but basically you want people to pull a system like this by selling their urine. Yeah. Okay.
And the chemical cost is just $100 for a whole year for one person's in urine, right? And the value of the fertilizer and in the end is at least 10 times more. So because you have that price difference, which you never have in any other sanitation system, if you build a septic tank, you pay for the septic tank, and then you pay for emptying. So as a household, you never have any return on investment. It's the same with wastewater treatment plants. Pay a monthly water fee to the municipality to treat something, but that's what we're trying to change a bit, where we're saying that for the first time, maybe there is a change in sanitation where you have a product that has real value that can then pay for sanitation or for anything else the household needs.
Sorry, I have a lot of questions. You line this tray with PVC, with plastic sheeting, 250 micron or what? And is that not from the heat and the, what's happening there?
So the system we tried in Goba Bev, it was that was used for 6 months. That was never replaced. So at the end, the dried urine was harvested, but the plastic sheet remained.
Yeah, so to answer that question, firstly, in terms of with this, because you have a polycarbonate sheet, you don't have UV degradation, right, of the sheet, and in terms of temperature, because you have the constant evaporation, you don't have high temperatures which can volatilize anything.
So the temperature above the urine in the air is around 60 degrees, but the urine itself is around 35 to 40 degrees because evaporation cools it down.
Materials plus minus about 2. That depends on who's constructing it. So it depends on volume. We for 10 units, we pay 2,000 in terms of labor per unit. And then when we spoke to the manufacturing, we're like, how much for the next 10? He said, okay, it's 1,000 for the next 10. So rapidly the price decreases. So if you imagine, like for us, we think we should do about 100 to 200 households before you really drive down manufacturing costs.
And I can just add that the fabricator who was building them for us, he built basically 2 units a day, 2 people.
Any other questions? If you have any further questions, I'm sure they would be willing to take it afterwards. With that, I think let's conclude the evening. Thank you guys for joining. Thank you to our speakers. It was very entertaining. Please feel free to use the bar at the back and have a safe evening. Thank you.